Good morning, everyone. And this is a class on optimization techniques, in particular on machine learning and data science tools. Okay. So the objective of optimization is to deal with various real-life problems, and that is in getting the optimal output for your problem, and that usually happens to get a maximum or a minimum of a certain function, and that has real-life applications. In the same manner, in machine learning also, optimization is applied. In general, while doing optimization, we know exactly what the data looks like, whereas there are areas that we want to improve this. In machine learning, we have no clue how our new data looks like, let alone try to optimize it. So the challenge is what the data looks like, and therefore in machine learning we perform optimization on the training data and check its performance on a new or what we call it a validation data. So there are various kinds of optimization techniques, such as, for example, in mechanics, it could be designing the surface of an aerospace design. In economics, it could be cost optimization or profit maximization. In physics, it could be time optimization in quantum computing or whatever. So various popular machine learning algorithms, such as linear regression, neural networks, k-nearest neighborhood, etc., depend upon certain optimization techniques. And one of the most common used optimization techniques in machine learning is the gradient descent. Let's have a look at how optimization is used in real life. For example, if you look at this picture, the optimal listening time for a student in a given lecture could be on the left side, you have the boredom. The student gets bored, gets tired, fed up. And on the right side, you have the understanding level. So the student's understanding in a given lecture increases for the first 10 minutes, okay? Here it's about 8 minutes and 25 seconds, and then it gets constant. Whereas the boredom increases as the lecture hour increases, the student gets bored more and more. So here the lecturer is expected to maintain the optimum time that the student can retain a given lecture, and that is on average about 8 minutes and 25 seconds. Let's have a look at another real-life example of optimization. As you can see in the picture below, there is a cow in the middle at the position 2,2. We are on the XY plane, Cartesian plane. The cow is tied to a rope of 1 unit long, which means the cow can move a maximum of 1 unit radius about its current position. So there is a grass at the position 4,3. So obviously the cow wants to eat this grass, but it's tied to a rope of 1 unit long. And there is also another perpendicular electric fence that passes through the point 2.52. So the question is, how close can the cow get to the fodder? So this problem will have its own objective and corresponding constraints to achieve that objective. So the framework, I have to put it on, yeah. So the framework of this, the variables, obviously, we are on the XY plane. So we have variables X and Y. That is we can see the position of the cow. The cow is now at the position 2,2, but as the cow moves, we'll be dealing with the other points on the plane. The objective is to keep a certain distance of the cow from the position of the cow from the grass. So that is the Euclidean distance between 2 points. So the position of the the grass is at the point 4,3. So the Euclidean distance would be x minus 4 the whole square plus y minus 3 the whole square under square root, but you can get rid of the square root because the distance, the minimum distance in the square root and the minimum distance without the square root is the same. So we can take this as objective function. What are the corresponding constraints? One constraint is the rope. It's of 1 unit length. So from the center where the position where the cow is located, again you have the Euclidean distance x minus 2 the whole square plus y minus 2 the whole square, which is less than or equal to -1. And the fence, vertical line x less than or equal to 2.5. So within this constraint, the cow can be as close to the grass as possible, and we want to find that distance. And this framework is the optimization, the way the optimization problem is modeled. So we want to minimize or maximize the objective, that is a function of variables, in this case on R2, subject to certain constraints. These constraints are also certain functions of those variables. And how can we do that? We can take unconstrained cases, for example, minimizing this distance. This is a distance function, where the cow starts at the position 2, 2. So if we assume the problem is not constrained, so the cow can move anywhere, a distance of 5, a distance of 10, a distance of 1. Okay. So the cow does not know where the grass is, for example. It knows exactly, knows only the distance from the grass. So there are two issues here. One is the distance from the targeted point, and the other is to which direction we should move to get to that point, because there are equal distances in any direction. So the issue of distance and direction go together. So it needs a good direction to move from the current point. So the key question in optimization is, what is a good direction? And what distance do we have to move towards that direction to get the desired point? Let's have a look at this graph. The graph of y equal to x squared plus 2, as you can see here, looks like this. We want to find the minimum of this function. So if you go to the current point, say for 0.8, it's to the right of the minimum point. So we should move to the left a certain distance to get to the minimum point. Okay, if we move the current point to 0.5, negative 0.5, then again, we are to the left of the minimum point. That means we should go certain distance to the right to get to the minimum point. The minimum point is around 0. So in general, if the current point is positive, we should move to the left. That means the desired direction is to the left of that point. If the current point is to the left, if it's less than 0, then we should go to the right. So by adjusting our direction, we'd get as close as possible to the desired point. So the new point x would be the current point plus the new direction. From the current point, we have to check towards which direction we should move to improve the minimum point. So if the current point is positive, we want the direction to be to the left, less than 0. If the current point is negative, we want to move to the right. Okay. So how can we choose this direction D? Okay. This is a function of one variable. So we can, in a function of one variable, we have only two directions, to the right or to the left. So there is no ambiguity. We can directly see that from the graph. But in general, for a multi-variable function, how can we choose the direction D? That leads us to the concept of derivative. The gradient, or the simple derivative of the function, gives us a clue about which direction we should move. So the derivative at the current value of x is twice of the current value of x. So the negative of the derivative does the trick, which means in the direction of the derivative, the function grows the most. That means it's in the ascending direction. Whereas in the negative of the derivative, we get the descending direction, because the function decreases most in the negative of the derivative of the function, or the so In this example, the current point is 0.5. So the negative of the derivative is minus 2 times 0.5, which is -1, which means we need to move in the negative direction. And that's correct. At the point 0.5, the minimum is to the left. So the negative direction is -1. So the new value of x would be the current value of x plus that direction, which is minus 0.5. So we need to update our value, which is the current value of x would be the new value, again 0.5. So it's a kind of iterative process. Again, we find a new direction at that point. So the negative derivative at that point is found to be now 1. That means positive direction. Because we are to the left of the minimum point, we need to go to the right direction to get to the minimum point. Again, we get 0.5. So what's the problem? The problem now is we are moving to the right and to the left to get to the minimum point, but we don't know the actual step size. We have to have a step size so that we can get as close as possible to the desired point. Because if we move back and forth without the actual step size, we'll end up moving around without achieving our target. So one is the direction and the other is the step size. So think about how you modify the step size at every step to avoid this problem. So the gradient descent algorithm looks like this. The first step is start at any position, usually randomly, or using certain techniques to have an initial point. And then the second step is find the gradient of the function, that means the objective function that we want to minimize or maximize at the current point. And then improve this current point through the gradient or the negative of the gradient and the corresponding step size. And then repeat this process until you get to the desired point. So gradient is a generalization of derivative, as I said before, to higher dimensions, okay? So negative gradient at the point 2, 2, for this example, is 4,2. So point towards the direction 4, 2 points towards the grass. And the negative gradient at 1, 5, 6 minus 4, it points towards the grass again. So gradient descent in general is the simplest unconstrained optimization procedure, and it's easy to implement, provided the objective function is, of course, differentiable, okay? If step size is chosen properly, it will probably converge to a local minimum. So think, why doesn't the gradient descent algorithm always converge to a global minimum? So a sufficient condition, the function needs to have one more property for us to be confident that the point is a global minimum. Otherwise, we'll get a local minimum point. So think about how to modify the algorithm to find a local maximum. I mean, whatever works for a local minimum, the same procedure works for a local maximum. So if you are working in a local maximum setting, then the gradient of the point, the derivative or the gradient of the function at that point, as I said before, points in the ascent direction. So we don't need to make it negative. We are making it negative because we want the descent direction. So can you come up with a method that picks a different direction than just the negative gradient? Yes. Okay, how about the constraint case? Real world problems are rarely unconstrained, okay? Usually, problems are associated with certain constraints. So we need to understand gradients better to understand how to solve them. Let's have a look at a function of one variable. So we'll have the Taylor series expansion of a function, okay? If we take the function at a point plus certain epsilon distance towards direction D, then that's approximately, exactly equal to the Taylor series expansion that you see here. So taking, removing the tail of this series for small epsilon, we have the function x plus epsilon times a certain direction minus f of x is approximately equal to epsilon times the derivative of the function. Taking certain errors by removing those terms with derivative 2 and more. Okay. So what should the value of d be such that this epsilon times derivative of the function is as small as possible? Okay. So that the difference of, so that the negative derivative is the direction of the maximum ascent, maximum descent. So it's important that any direction such that the derivative of the function is less than 0 is a descent direction. Okay. So if you look at this function of two variable, that means, as you can see, the surface. So the steepest direction and the steepest descent and ascent are as given below. So any direction such that the derivative times the gradient of the function is negative is the descent direction. You can see that the red line shows that the derivative, in that direction, the transpose of d times the gradient of the function is 0, and it's positive in the upper half space and negative in the lower half space. So in general, a constraint optimization is minimizing a certain objective function such that the constraint set is given as g of x equal to 0. So given a point x, the descent direction is any direction which will lead a point x bar such that f of x bar is less than f of x. For all other x's in the neighborhood. And the feasible direction is any direction which will lead to a point x bar such that the constraint set is satisfied, that is g of x equal to 0. So if somebody gives you a point x star and claims that it's a solution to this problem, what properties does this point have? These are called necessary conditions. So it must be that the constraint set should be satisfied, and there must not be a descent direction that's also feasible. So there must not be a descent direction which is feasible. Look at this. So the gradient of the function at x star is given here, and the derivative of the function, the gradient at x star, is also given here. So the direction of the gradient of the function at x star and the gradient of the function at g star are opposite, they are in opposite direction. So the gradient of the function at x star is equal to minus lambda times the gradient of the function at g star. So this is like a necessary condition. So we can convert a given constraint problem into an unconstrained optimization problem by attaching that value f of x equal to lambda times g of x. Okay, so the problem would be these lambdas are the Lagrange multipliers. So any constraint problem could be written as an unconstrained problem using this Lagrange. For example, in training neural networks, we have the loss function, optimizing the loss function. So the target is applying the DL model these days are trained with a variant of the gradient descent algorithms. So the GD, or gradient descent, applies an iterative refinement of the network parameter theta. And therefore, by doing this, following the same procedure, the gradient of the loss function gives the direction of the fastest increase of the loss function, the L of theta. So the loss function for the DL tasks are defined over a high dimensional space. So this makes the loss function impossible to visualize. So we can still gain intuition by studying one-dimensional or two-dimensional examples of the loss function. So the gradient descent algorithm, once more, we randomly initialize the model using certain parameters and compute the gradient of the loss function, and then improve the current position by choosing the proper step size and direction, which is the steepest descent direction, which is a negative of the gradient of the function. And that step size is usually referred as a learning rate. So we repeat the process until a terminating criteria is achieved, and that terminating criteria is tolerable error. Like if you look at this loss function, the initial weight is given here. So depending on the choice of the learning rate, if the learning rate is small, would the number of iterates would increase. If the learning rate is not as such small, then we'll move back and forth. Okay. So if you look at this example, we started at theta naught, and we found the direction, which is in the negative of the gradient of the function. We improve the current theta, and then we repeat the process. We are moving towards the desired minimum point. So eventually, we'll reach at a minimum point. Again, the gradient descent algorithm stops when a local minimum of the loss function is reached, or when that criteria is achieved. So it does not guarantee reaching a global minimum. Usually, we'll end up trapped at a given local minimum point rather than. However, empirical evidence suggests that the gradient descent works well for neural networks. Okay, in particular, if convexity condition is also satisfied. I mean, if the function is convex in the given domain, where local minimum would be global minimum. Okay, with convexity condition. That's why we have seen convexity earlier. For the most part, the loss function is highly complex and usually non-convex. That's a problem. As you can see, this graph, it's a non-convex graph. So randomly initialize neural networks, the NN's results in differential initial parameters. So the gradient descent may reach different minimum at every run. Therefore, NN will produce different predicted outputs. So currently, we don't have an algorithm that guarantees reaching a global minimum. At least we know that there is a local minimum, that's not for an arbitrary loss function. So the other topic that we need to cover is nonlinear programming part. So if either of the objective function or one of the constraints is found to be nonlinear, then the problem is a nonlinear optimization problem. As an example here, you have a function f of x equal to this, where there is a square term. In fact, the constraints are linear. So if any of them are nonlinear, the problem is nonlinear optimization problem. So in general form, the nonlinear problem is given in the following form, where there is an objective function, there are constraint sets, and there are non-negativity conditions. So there are many types of nonlinear programming problems. In this particular case, you have the objective function is linear and the constraints are linear. When it's linear, you can on R2 you can use the graphical methods. You can have the feasible region, the extremum points, and the likes. And for Rn, I mean, when n is greater than 2, you can use linear optimization techniques like the simplex method and the likes. Okay. So, for example, when the constraint set is nonlinear, you have such a region. I mean, the feasible region may look like this. When the objective function is nonlinear, the constraint set is linear. You have the feasible region, but the line is, the objective function is nonlinear. You have also another function here. So local maximum, as I said before, local maximum or local minimum need not be a global maximum or minimum unless the sufficient conditions are satisfied, such as convexity, usually. So this function has 3 local maximum points at the point x equal to 0, x equal to 2, and x equal to 4. But only one of these can be a global maximum. And the same is true for the global minimum. So nonlinear programming algorithms usually does not distinguish between a local optimum solution and a global optimum solution. So that means we need to talk about convexity of the function, because that gives us a sufficient condition. Convex function is, we have defined already a convex set. So a convex function defined on a convex set satisfies this inequality. The functional value on the line segment of is always less than or equal to the segment joining the functional values. So lambda is between 0 and 1. So this function, this inequality is how we define a convex function. If a function is convex, the negative of the function would obviously be a concave function. So the geometric interpretation indicates that the function is convex. The inside of the function is epigraph of the function is a convex set. Okay, whenever the function is convex, this we have seen already. So there are tests. When they mention class. I mean, I'm sorry for the interruption. So there are various tests for that. First derivative and second derivative tests for the I mean, for those points that could potentially be a minimum or maximum points. The convex, convexity test for a function of a single variable. Here you have second derivative needs to be positive. I mean, whenever you have a minimum point, you can recall a function of one variable. For a function of two variable, you can see that this is a convex function, and the local minimum would be a global minimum. If you have a strictly convex function, then you have a unique optimum point. Okay. An affine function is both convex and concave. And there are functions which are neither convex or concave. Okay, the concept of convex or concave functions of a single variable also generalized to a function of more than one variable. Thus, if a function f of x is replaced by a function of more than two variables, then the definition still applies to x when x is replaced everywhere by more than one. So similarly, the corresponding geometric interpretation is still valid after generalization of these points. So what's the line segment? The line segment joining any 2 points on Rn can also be taken. So the definition, in general, f of x is a convex function for a setting in Rn. If for each pair of points on the graph of f, the line segment joining these 2 points lies entirely above the graph of the function. Okay, so the functional value lies below the graph of that line segment. So the convex test for a function of 2 variables is the second partials. You find the second partials, and these 3 conditions should be satisfied. Let's have a look at this example. You can see that the function is has a nonlinear function. So the 3 conditions are satisfied, except that the first one is not strictly greater than 0. So when there are 2 variables, the convexity test for generalization of is given here. For example, in the mathematical terminology, the function is convex if you have an NN Hessian matrix, which is positive semi-definite for all values. So there are 2 important properties of convex and concave functions. If a function is convex, then the negative of the function is concave, and the vice versa. And the sum of convex functions is convex. There are properties associated with convexity. The sum, also the finite intersection of convex functions is convex, and the vice versa. The sum of concave functions is concave. I mean, whatever works for a convex function, all the properties works for a concave function. So to illustrate this, if you take these 2 functions, f1 and f2, they are both convex functions. So you can verify by calculating the second derivatives and the conditions given earlier. Therefore, the sum of the functions is also convex. You can check the condition once again. And hence the negative of the function is concave. Okay, so how about a convex set? So a convex set is again a collection of points such that for each point is a collection. The line segment joining the 2 points is also in the collection. So if you take this set, for example, this is convex. This is also convex. I mean, the left one is not convex. The right is convex. So condition, the reason why we are talking about convex sets and convex functions is to guarantee that a local minimum is a global minimum, and the same is true for local and global maximum points. So the condition for a local optimal solution to be a global optimal solution in a nonlinear programming problem without constraints is that if a nonlinear programming problem has no constraints, then the objective function being concave, okay, guarantees that a local maximum is a global maximum. If it's convex, then a local minimum is a global minimum. On the other hand, if a non-linear programming problem has constraints, then both the objective function being concave and the feasible region being a convex set, in fact, the feasible region needs to be always convex. It guarantees that a local maximum is a global maximum. And if the objective function is convex, then a local minimum is a global minimum. Otherwise, we end up, we will be trapped in local minimum or local maximum points. So for any linear programming problem, on the other hand, its linear objective function is both convex and concave. And so its feasible region is again convex. So its optimal solution is certainly a global optimal solution, okay, in the case of linear programming problems. So in general, the feasible region for a nonlinear programming problem is convex set whenever gi of x are all convex. As I said before, if you have a set of convex functions, the intersection is convex. If all the functions, the gi's, are convex, then the intersection is convex. The region formed is convex. So that's what you see here. So let's have. So this region is not convex, as you can see easily, but the one on the left is convex region. So for a convex region, the optimum point is achieved at the point 26. Whereas the region on the right, the feasible region, is not a convex region. So we cannot be sure that that point is whether it's a local minimum or a global minimum point. So the extreme point of a convex set is a point in a set that does not lie on any line segment that joins the other 2 points. So you have extremum points here, A, B, C, D, E. Why we cannot form them as a convex combination of the other. So the classical optimization methods: unconstrained optimization of a function of a single variable. As you can see, consider a function of a single variable. The necessary condition for a particular solution x to be either a minimum or a maximum is that the derivative of the function is 0. So that's a necessary condition. It does not mean that, I mean, as you can see the graph, the global minimum is at A, and you have local minimum at D, local maximum at C, global maximum at E, and inflection point at the point B. If the second derivative is positive, then x is a local minimum. F of x is strictly convex in the vicinity of x star if the derivative is 0. And that's a necessary and sufficient condition for the point x star to be a local minimum, as I said before. So global minimum at A and global maximum. If the function is strictly convex anywhere, then there is only one local minimum and one local maximum. Unconstrained optimization of a function of several variables. So the analysis for an unconstrained function of several variables is similar. Thus, a necessary condition is that the partial derivative should be equal to 0, and hence the gradient at that point will be equal to 0. Otherwise, everything is the same. Constrained optimization with equality constraints, as you can see here. We have the classical method of dealing with these problems called the method of Lagrange multipliers. And this procedure begins by formulating a Lagrange function. So we can convert a given optimization problem, constrained optimization problem, into unconstrained optimization using the Lagrange multipliers. We will see an example below. So given this function, h of x equal to, x1 and x2 equal to x1 square plus 2x2 minus lambda times x1 square plus x2 square minus 1. So in a linear function, we can deal with we can see the partial derivative of this function with respect to each of the variables, and of course the Lagrange multiplier lambda. They all need to be 0 because this is a necessary condition. So we find the point x1, x2 to 2 points satisfying these 3 conditions, where the function is positive and negative at the corresponding points. So types of nonlinear programming problems. Nonlinear programming problems can come in many different shapes and forms, and no single algorithm can solve all these types of problems. So unconstrained problems, the necessary condition is the gradient of the function at that point needs to be 0. When f of x is concave, the condition is also sufficient, whether it's convex or concave. So when solving X star, it reduces to solving the system of n equations by obtaining n partial derivatives. That means dealing with the gradient of the function. If there are constraints such as the non-negativity constraints, again, the optimum point will be changed. You can see this example. How about convex programming? With the assumption of convex programming, when f of x is concave and each constraint state is convex, these assumptions are enough to ensure that the local maximum is a global maximum because the function is concave. Okay. So linearly constrained optimization, special case is convex programming. We have the simplex method and the likes. And there are also quadratic programming problems, separable functions. There are a variety of such and non-convex programming problems also. So one variable unconstrained optimization. For one variable case, you can see that this is a concave function where the derivative is 0 at a given point. Because it's concave, the optimum is unique. So the entire process of, we can also apply the midpoint for the bisection method numerical techniques as given here. Okay. So you can use iterative techniques, like you find the derivative of the function and then update the value of the function at a given point until you get the desired point. So the function f of x is given here. So the first derivatives, the first two derivatives are as given here. So the second derivative is positive. That means, it's negative at 0, at x equal to 0. And hence it's a concave function. So the initial points, if you take x equal to 0 and then 2 with their midpoints, the midpoint of 0 and 2 is 1. So you can do this is called the bisection method. Okay. We can move back and forth until we get as close as possible to the desired point. So multi-variable unconstrained optimization problems follow the same procedure. So gradient descent optimization, the gradient search procedure, I've already explained earlier. You can see you initialize, select epsilon, as a stopping criteria for any initial point x bar. Go to the stopping rule and then iterate by finding the functional value at t. You update the value and then substitute these expressions into f of x. Okay. You can take an example, maximizing this function. The partial derivatives are given here. So the gradient procedure gives us the gradient of the function at 0, 0. If you select the initial point to be 0, 0, the gradient of the function at 0, 0 is found to be 0 and t. Okay. Then you find, okay. So this is how it goes. This is the application of the gradient procedure. We have already seen it earlier. So as you can see the picture below, we move from 0, 0 to 0, half, and then the perpendicular direction towards this point, and then vertical, then horizontal, vertical, until we get close to the point x star, which is an optimum solution. Okay, so the gradient descent method already discussed. So the other is the KKT conditions for constraint optimization problems, where we include the Lagrange multiplier. So I will attach you so these are all the partial derivatives, including the Lagrange multiplier conditions, should be 0. Okay, these are the examples. So if we want to maximize this function of x and y subject to the constraint, so the corresponding the necessary and conditions are given below here. So we come up with, okay, the values. Okay. Another example. So that's it. Have a look at mainly focus on the gradient descent method for especially our concern. So that's it. Thank you very much.